Mechanism of the reaction in this experiment is a free radical bromination of the benzylic carbon in ethyl benzene. So in ethyl benzene, the structure is shown on the right side. There is a benzylic carbon, which is the carbon directly bonded to the benzene, and you have two hydrogens bonded to that benzylic carbon. In the free radical bromination, there are three steps. First step is initiation, second step is propagation, third step is termination. Dibenzoyl peroxide is the free radical initiator. The bond, which is the oxygen to oxygen bond, which is the peroxide, is easily cleaved upon heating. So the molecule will split symmetrically, forming two molecules of a free radical on the oxygen. This free radical on the oxygen will initiate the propagation step, in which it will now react with NBS and bromosuccinimide, forming Br dot or bromine free radical, and a byproduct, which is the N-benzoyl oxysuccinimide. The Br dot will now react with the benzylic carbon and ethyl benzene, forming HBr and resonance stabilized intermediate, which is the free radical on the benzylic carbon. You can write several structures because the free radical on the benzylic carbon can be delocalized on the benzene, stabilizing that free radical upon delocalization on the benzene. For a free radical reaction, the curved arrow is a half-headed curved arrow showing the movement of electrons. The HBr generated will now react with another NBS, forming Br2, which is a liquid, and then a succinimide byproduct is also formed. So there are two byproducts, organic byproducts. The first one is benzoyl oxysuccinimide, and then the other one is succinimide. The Br2 generated will now react with the benzylic carbon from ethyl benzene formed in the second step, forming the first product, which is the alpha bromoethyl benzene, and then another Br dot. The Br dot will react with the other hydrogen on the benzylic carbon, abstracting that H, forming HBr, and then a free radical again on the benzylic carbon. So this benzylic carbon contains a free radical which can also be stabilized by resonance because this free radical can delocalize in the benzene ring. This free radical can now react with another Br2, brominating the benzylic carbon, forming the alpha prime dibromoethyl benzene and another Br dot or bromine free radical. We now have two products coming from ethyl benzene. First one is alpha bromoethyl benzene, and the second one is dibrominated product, which is the alpha prime dibromoethyl benzene. The Br dot or the Br free radical will now be terminated by reacting with itself, forming another Br2. Experiment 9 is about synthesis of alpha bromoethyl benzene. So the purpose of the experiment is to synthesize bromoethyl benzene and determine percent yield of product by NMR. So the reaction is shown in here, and then the mechanism is also shown in the handout. And then we are now going to set up the experiment. This is the experimental part, and then we are going to use the microkit. It's a simple setup, and we are going to mix together the reactants, NBS, and bromosuccinimide, ethyl benzene, and cyclooctane, the solvent, carbon tetrachloride, and then the initiator, dibenzoyl peroxide, and then one boiling chip. We are going to reflux it for 45 minutes. And then we are going to work it up. This is now the microkit, and then I am going to, I will now set up the experiment, and I will assemble the setup, and then I'm going to be using the round bottom flask, long neck. And then I'm going to use the adapter. I will now assemble the trap for the HBr that is being generated, the gas that is generated during the reaction. So I will take a 22 gauge needle. And then I'm going to get a septum here, and then I will attach the needle. So just be careful. And then I will attach it to the Teflon tubing. And then I'm going to put it, this is the air condenser, and I'm going to invert it. So that is our setup. Okay? So I will put this on top of the RBF. This is now the reactant, which is NBS. So I weighed 0.620 grams of NBS. That's bromo. That's N-bromosuccinimide. This is our brominating agent. So it's white powder. And this is the original container. N-bromosuccinimide. So write down the weight, please. The other reactant is the dibenzoyl peroxide. So this is the container. And this is the initiator. And I already weighed 0.010 grams or 10 milligrams of the reagent. And it's actually a very small quantity. It's a very small amount. So this is now what I weighed, and on the right side it's the NBS, and that's 0.620 grams. And then on the left side is the dibenzoyl peroxide, and you can see that it's very small quantity. It's 10 milligrams. It's the initiator. So this is now our NBS on the right side. This is 0.620 grams, and then this is the dibenzoyl peroxide, and that's 10 milligrams. So dibenzoyl peroxide or benzoyl peroxide, and then N-bromosuccinimide. This is our brominating agent. The peroxide is the initiator. So I'm now going to put it into the, I will now put it into the flask. So I have the round bottom flask, and I have the boiling chips. And then I will now put inside the RBF. And I use a funnel because the mouth is small. Otherwise, it might spill. And then I'm gonna push it. And then I'm going to add the 10 milligrams of the benzoyl peroxide, very small amount. And then I'm now going to add the ethylbenzene cyclooctane mixture. It's 80% ethylbenzene, 20% cyclooctane. And I need 0.4 ml. So about 0.4 mil. So this is about 400 microliters here. So I'm just going to introduce it. So I got everything in. And I'm going to rinse this with the solvent. So the solvent is carbon tetrachloride. So carbon tet is the solvent. And so it's about 0.8 mil. And I'm just going to approximately use this graduated pipette. So this is about 0.75 mil, so a little bit more. And the solvent, I can add a little bit more, so approximately 0.8. So I want to rinse the funnel so that everything is in. And then I also rinse the side here. So that is now our setup. So I'm now going to attach the air condenser that I assembled earlier, and I also have the adapter in here. So I'm going to attach the adapter, rubber adapter, and it will snap gently, and I'm going to attach it on top. So I'm going to attach the trap. So this is a micro scale trap of the HBr that is being generated. So this is just the conical tube from the micro kit. And then I'm going to attach this inside, and then I have a cotton. So I'm going to moisten the cotton. So this should be below. So I will moisten the cotton with water. So this is just RO water. So I soak it so that the HBr will get absorbed into that cotton. So I don't want the end of the tube to be immersed in that water, because there's going to be a back pressure. So the HBr gas will get absorbed into the water. It's just basically acidic. And then, so I want to trap it so that it's not like all over. And I'm also under the hood. So let me repeat it. So this is our reaction mixture. And then this will be refluxed. So our mixture in here, we now have, first we have the NBS and bromosuccinimide. We have the peroxide, which is the initiator, and we now have the ethylbenzene, which will react to be brominated, and then the cyclooctane act as a standard, because we want to quantify the amount of the product that is being produced after bromination, and then the carbon tetrachloride is just the solvent. So we have 5 things in here. So we're now ready to reflux, and I'm going to lower it down into the sand bath. So I'm going to set it so the sand bath is connected to the transformer. Connected to the transformer, I'm going to set it to 120 volts, and I'm going to set it first to about 35. So I want to see this refluxing. So I'm gonna lower it a little bit more. So I don't want the bubbles to be going up so high. So I can raise it higher. So that's why I have it in a jack. Or I can also raise the clamp up if it's too much into the sand. So this is our setup. Once it starts to bubble and reflux, we are going to time it for 40 minutes for the reaction to go for the bromination reaction. So this is the adapter, and then I have the air condenser so it doesn't dry up, and then I have the needle, and then I have it, so it's not entirely enclosed because I have the outlet to the Teflon and then into the trap, which will collect the HBr that is coming out from the reaction mixture. So you can see the bubbles right now, so I increased the setting for the transformer to about 45, and now you can see the bubbles forming, but I want to watch the bubbling so that it doesn't go up and it stays at the bottom. So I constantly would take it out and then shake it so that to make sure that I'm mixing the reaction mixture. So occasionally I would do this. So we let it reflux for another half an hour, and then we are now going to do the next step. So it's been refluxing for 40 minutes. I'm now going to disassemble the setup, and we are now going to do the workup. So I will now turn off, and then I will take it out. Okay, I will now take out the setup. And I will allow it to cool. The next step is to filter. And I'm going to set up a filtration using a little bit of glass wool. So this is glass wool. And I have here 2 pipettes, and then it's a pasture pipette, and I'm going to use a boiling stick, and I will put a little bit of the glass wool inside. So that's my filtration setup. And I also have a vial. So we'll filter through the vial. So this is our reaction mixture over here. And I'm going to use the pipette without the glass wool. And I'm going to use a bulb. So I put the bulb in here. pipette. And then I'm now going to pipette. So I will take the liquid so I don't want the solid, so I'm going to filter. So I have another pipette, and then into the vial. So you can see that I'm filtering the solid byproduct. So I should have enough for the NMR. So I push it in so I can have enough sample. So that is our NMR sample here. So this is our NMR sample. We are now doing the analysis part of the experiment, and this is the NMR sample that I filtered. So it's filtered, it's just a liquid. I filtered out the solid byproducts, and then I'm now going to put it into the NMR instrument. And again, I have a syringe in here, so I'm gonna withdraw about 200 microliters. So this is half a ml, and I'm gonna use this to withdraw. So about 200, but I have enough sample. Okay, so I kind of tap it. So I tap it so that the bubbles go up. So I inverted it like that, and then I will try to remove the bubbles. Okay, and now I'm going to inject into the inlet port, and this is the outlet port. So we wanted to get like 8 drops out of the outlet port, so that I push the sample out of the instrument. So there's a loop inside the magnet, and it accommodates about 20 microliters. So now I'm going to gently inject it into the inlet port. There's a Teflon tubing, and then I slowly push it so that, watch the drip. So I wanted like about 8 drops. So I have enough in case I need to inject more later. So I will just cap it. So we are now in the NMR instrument, and I put now a run name, which is bromoethylbenzene. It's the brominated ethylbenzene. And again, this is the frequency of the instrument. It's a low field magnet, 45 megahertz. And then I'm just gonna do 8 scans. And then I'm just gonna do start run over here. So I click on it, and now we are running. So there are two parts for the NMR is to acquire. So that's the acquisition portion. And then the second part is the processing portion. This is now the raw data. This is called the FID, which is the time domain. As you can see, the X scale is in milliseconds. And this is kind of a rough conversion of it into a frequency domain. So we are now going to process the data. So the next step is processing the data. And I'm now going to download data. So I'm going to download data and I click on it. So this is now again the raw data, which is called the FID, free induction decay. And we are now going to process it from a time scale, so time domain, into a frequency domain or a frequency scale. So I will do first what is called zero filling. And again, all of this is in a manual, so you can just basically follow what I'm talking about in a written manual. And all of this is basically just processing. And that's line broadening. And I will now process what is called a Fourier transform, converting it into the what is called the frequency scale or the chemical shift in ppm. So this is what is called phasing. So I put it upside down. And I will zoom it. So zoom it. And that is basically our spectrum. I will make the baseline nicer. Just make it more flat. And I am now going to reference the peak. And I'm just going to use a generic peak, which is ethanol. And I'm now going to manually assign the peaks. And this is our peak of interest. This is the cyclooctane, and this is part of our molecule. This is coupled to this one. So this peak here, which is a quartet, is coupled to the doublet, while this one is by itself. So I'm going to manually label that peak. So I'm labeling each peak. And then this would be the aromatic or the benzene peaks. Note that this NMR spectrum has 3 compounds in it. So it goes from around 1 ppm, and this is about 1.48 to 1.63, and this is 2.5 ppm, and this is 4.45 to 4.91 ppm, and this would be the aromatic region at about 7 ppm. So the next step is to do integration. So I will now do the integration, and I know these 2 peaks are coupled to each other, so I'm going to assign this as 3. So I will do 3, and that would be coupled to that one, and that's about 0.7 or 1, because there really is no 0.7 proton. It's going to be a whole number, so that's 1. And then this is going to be by itself, and that's 0.3. So that's the integration. So it's a ratio. So let me just do this part here. So that's around 3. So this is around 3. So this is the ratio, but this is by itself. Again, this is cyclooctane, and this peak here and that set of peaks, quartet and doublet, are coupled to each other. They're in one molecule, but this is by itself. And then the benzene, you have a lot of benzene in here. So that's about 5. Okay, and then so that is our NMR spectrum. So I will now print this out, and the class will get a copy. So this is now the hard copy of the NMR for experiment 9.